This video will cover section 4.4 on properties of definite integrals, additive property, average value, and we're not going to cover moving averages, so just additive property and average value. Okay. All right, so objective, use properties of definite integrals to find areas between curves, similar to finding what we just did with which is considered area under a curve. Solve applied problems involving definite integrals, and then determine average value of a function. All right, so theorem 5. For a less than b less than c, in other words, a is the beginning, c is the end, b is somewhere in the middle, the definite integral from the beginning to the end, from a to c of f of x dx, is equivalent to finding the definite integral from a to b of f of x dx, and then adding the definite integral from b to c of f of x dx. In other words, for any number b in between a and c, we can split up your function into pieces. So you can go from a to b, calculate that value, and then from b to c, calculate that value and add them together. That's not always necessary, but we will have a need for needing to do that, particularly when we have piecewise functions. All right. So we're going to find the area under the graph of the function y equals f of x from -4 to 5, where our function is defined as the piecewise function f of x equals 9 if x is less than 3, and it's equal to x squared if x is greater than or equal to 3. So if I were to graph this function, this is what it would look like. So notice here my problem, I'm finding area between -4 and 5. So if I start at -4 on the x-axis all the way to 5. So my function is defined for any x's less than 3, the value is 9. So way out here at -4, that's an x value less than 3. Our function is a constant value at 9, so a horizontal line up here at 9, and that would extend all the way up to the x value of 3. Okay, for x is 3 and bigger, we follow the graph of x squared. So if I plug in a 3 here, I get 9, right? 3 squared, so it meets up with where this one stopped. And then my x squared is this side of this parabola, right? Or just this piece of it. And that stops at 5 since we're asked to stop here at 5. So when x is 5, 5 squared, 25 would be way up here. So if I cut off vertical lines between the -4 and the 5 and just look at what that graph looks like between these two x values. So this would require a need for the previous theorem, because we're going to have to integrate from -4 up to 3 by utilizing the function value being 9, and then integrate from 3 to 5 because we have a different function definition in that space, and then add them together. All right, so the integral from -4 to 5, utilizing that theorem, says I can do the integral from -4 to 3, and then add the integral from 3 to 5. And I cut it at 3 because that's where my piecewise function changed definition. So from -4 to 3, that applies to the function definition being f of x equals 9. And then after 3, from 3 to 5, those values of x correspond to the function definition being x squared. So my antiderivative here is 9x from -4 to 3. My antiderivative here is x cubed over 3 from the 3 to the 5. So the 9, we plug in 3, minus, then we plug in 4. So plug in the top, minus plug in the bottom. Plus, do the same here, plug in the top, 5 to the 3rd over 3, minus, then plug in the bottom, 3 to the 3rd over 3. Clean it up, you get 95 2/3. Okay, here's another one that is similar. If you want to try this one on your own, pause the video, try to do it using the previous example, and then press play on the video to check your answer. Find the area under the graph of y equals g of x from -3 to 6, where g of x equals x squared for x values less than or equal to 2, and it's equal to 8 minus x for x values greater than 2. So if I'm going to integrate from -3 to 6, right, 2 is in that space. So I'll have to go from -3 up to 2 using this as my function, and then go from 2 to 6 using this definition as my function. Okay, So negative 3 to 2, then from 2 to 6, because we split it at 2, because that's where this splits. So between negative 3 and 2, in other words, for x is less than or equal to 2, we're using x squared. And then from 2 to 6, where x is greater than 2, I'm using the 8 minus x. So this antiderivative is x cubed divided by 3, and then I'll evaluate between those limits, plus this antiderivative would be 8x minus x squared over 2, and that will be evaluated between the 2 and the 6. All right, so then we just do our plugging in. Plug in a 2 here, minus, then plug in the negative 3, plus, then plug in 6 into here, minus, then plug a 2 into there. Clean it up, simplify, and you should end up getting 27 2/3. Okay. Next example, evaluate the integral from 0 to 7 of the absolute value of 2x minus 1 dx. So anytime our function is given as an absolute value of something, that means it's a piecewise function. So our first step would be to rewrite this function as a piecewise function. All right, and here's how that works. The absolute value of 2x minus 1. All right, so the breaking point of the two pieces is the value of x that causes this expression to equal 0. So if I were to set 2x minus 1 equal to 0, I would get x equals a half. So for x is greater than a half, it's just that function with no absolute value in it. For x is less than a half, it's the opposite. So it's basically negative 2x plus 1, changing the signs of both. So negative 2x plus the 1, right, is the same as positive 1 and a minus 2x. So you leave it as it is for x is greater than the value that makes it 0, and you change the signs of all the terms for the x's less than that number. So notice here we're going to integrate from 0 to 7. So our breaking point being a half means from 0 up to a half, those would be values less than a half. So that means integrate this one. And then from a half to 7, those values are greater than a half, right? From the 1/2 up to 7, that means I'm going to be using this one. Okay, we're going to use our piecewise technique. All right, so 0 to a half, we use the one that we had written on the bottom. And then from a half to 7 was the one that we had written on the previous slide on the top. So we get x minus, this would antiderivative be x squared over 2, with the 2's it cancels, just giving me the x squared. From 0 to a half, here it's the x squared comes first, minus x. From a half to 7, plug in a half, minus, plug in 0, plus, plug in 7, minus, then plug in a half. Clean it up, simplify, and you get 42 1/2. Okay, so those first few examples are how to deal with piecewise functions and then absolute value being a piecewise function. All right, theorem 6, we're moving on here to dealing with area between two curves. So here we have two functions f and g, continuous. Suppose that f is the larger of the two. It will matter which one's bigger. So f of x is greater than or equal to g of x, so meaning on a graph it's the one above, over the interval from a to b. Then the area of the region between them is found by taking the definite integral between a and b and taking the function that's on top, f of x, subtracting the function on the bottom. And the reason for that is if I just did the integral of f of x, it's the area underneath f of x all the way down to the x-axis. So I'd be including all this stuff. So I got to subtract out, I have to subtract out the area underneath g, right, between the x and the x-axis. So if I just integrate f minus g, that'll just give me the area in between. All right, so find the areas of the region that is bounded by the graphs of f of x equals 2x plus 1 and g of x equals x squared plus 1. All right, so the first thing I need to do is look at the two graphs. Okay, so if the graph's not given, you'll have to use your calculator to generate a graph of your two functions. So the 2x minus 1 is this line right here, and the x squared plus 1 is this parabola down here. So it looks like f of x is on top of g of x. Okay. The second step is to find the points of intersection, right? It just said find the area between the two. It didn't give me any a's and b's. So I need to, if they don't give you the endpoints, you have to find them. So set f of x and g of x equal and solve. So 2x plus 1 equals x squared plus 1. So the subtracting 1 from both sides, they cancel. And if I subtract the 2x over here, we could rewrite that as x squared minus 2x equals 0. Factor out x, and we get 0 and 2. Okay. All right. So now we're going to compute the integral. So on 0 to 2, f of x is the upper graph. It was the one on top. So the integral from 0 to 2, the line was on top, minus the parabola was on bottom. Make sure you put the second function especially in parentheses because you're subtracting, that will matter. So if you clean this up and distribute your negative sign, you get 2x plus 1 minus x squared minus 1. So if you have a 1 and then a minus 1, they cancel. And otherwise you have a 2x minus an x squared that's left over. So just cleaning it up first. Antiderivative, 2x squared over 2 means the 2's canceled, just leaving the x squared minus x cubed over 3 from 0 to 2. Plug in 2, plug in 0, subtract, clean it up, you get 4/3. Okay? All right. Definition of average value. Let f be a continuous function over a closed interval. When you're needing to calculate the average value, denoted y subscript av, so the average value of y, over the interval from a to b, you find your definite integral, which we've been doing a lot of in the last few sections, but you're going to multiply that by 1 over b minus a. So b minus a is the length of that space. So 1 over that length, in other words, taking the definite integral and dividing it by b minus a, basically, that's your average value. So 1 over b minus a times the definite integral from a to b of f of x dx. All right, find the average value of f of x equals x squared over the interval from 0 to 2. All right, so 1 over b minus a, 2 minus 0, times the definite integral from a to b of the function. So 1 over 2 in the front, this is the 1/2. Antiderivative here is x cubed over 3 from 0 to 2. So plug in 2, plug in 0, subtract. So this is 0, this is 8/3, so 1/2 times the 8/3, 4/3, or 1 1/3. Okay, the visual of what that means is here's your function, x squared between 0 and 2, so this whole shaded piece here is your area under, that's the definite integral. The average value, which was 1 1/3, so this is where that's marking this at 1 1/3, right? Showing you where that average value hits right here. So it's actually true that the area under this space right here, that's kind of in this brown color, is equivalent to the area of this rectangle right here. Okay. All right. Next example. Rico's speed in miles per hour, t minutes after entering the freeway, is given by this velocity function for t values less than or equal to 30. From 5 minutes after entering the freeway to 25 minutes, so between time values of 5 and 25, what was his average speed or average value? Okay, so average speed, so average value, 1 over, we're going between time value of 5 to 25, so b minus a is 25 minus 5, times the antiderivative from same endpoints, 5 to 25, of the velocity. So 25 minus 5 is 20. So this is 1 over 20. My antiderivative, t to the fourth divided by 4, makes this an 800. Keep the negative. T to the third divided by 3 cancels the 3 on top. So 120 of t to the third. T squared divided by 2 multiplies this 8 by 2. So a 16 with the 3 stays on top. And then 60t. Evaluate between the endpoints. So plug in 25. They've just gone ahead and simplified it. They plug in 25. They're getting this number. Minus, when they plug 5 in, they get this number. It's probably easier to do that part on your calculator rather than having to write all those steps out. And then clean it up. 68 3/4 miles per hour. So average value. All right. So if you want to try this one on your own, pause the video. Use the last example we did as a guide and see if you can solve this one, and then you can play the video to check your answer. The temperature in degrees Fahrenheit in Minneapolis on a winter's day is modeled by this function. X represents the number of hours from midnight, so 0 up to 24. Find the average temperature in Minneapolis during this 24-hour period. So average value. All right. So 1 over, we're going 0 to 24, so b minus a is 24 minus 0 times the definite integral from 0 to 24 of our function. All right, 1 over 24 in the front, antiderivative x to the fourth over 4, plus the x cubed over 3, those coefficients just stay there, minus x squared over 2, keep the coefficient, minus and then 10.1x. From 0 to 24. Plug in 24. If you plug 0 in, notice everything is 0. So they've just shown the plugging in 24. It's technically minus 0. Clean up each term and then evaluate to simplify, and you get negative 2.5. So the average temperature or average value of temperature over that time frame is negative 2.5. All right, so in this section we talked about the additive property of definite integrals. States that the definite integral can be expressed as the sum of 2 or more. That's helpful when dealing with piecewise functions that change definition at a given point in the middle. The area of the region bounded by the graphs of two functions, f and g, where f is the larger function, is found by integrating from a to b of the top f of x minus the bottom curve g of x. And then average value is found by taking 1 over b minus a times the value of the definite integral from a to b of f of x dx. Okay, that then is the end of section 4.4.